Today we're going to talk about the 6 trigonometric functions. We're going to base our conversation on acute angles, and we're not yet going to bring into the conversation obtuse angles. So real quickly, acute angles would be angles between 0 and 90 degrees, or if we're working in radians, between 0 and pi over 2 radians. We're going to need to be comfortable with both of these unit measurement systems. We also are going to discuss 6 here, which might seem new to a lot of people because we for a long time have known SOHCAHTOA, which involves the 3 primary trig functions of sine, cosine, and tangent. But today we're going to introduce 3 new ones. Another piece of background information that's going to be necessary are some Greek letters. We're going to use Greek letters to label angles. The primary one I've used so far is theta. Some others that we will see will be alpha, beta, gamma. There's going to be plenty of others along the way, but those are the 4 primary ones that we're going to use today. Another thing that we're going to do today that's going to be a little bit of reverse logic is we're going to work in standard position for this angle. This angle that we're going to discuss today will come out from the positive x-axis and go counterclockwise. This will be the angle theta that we're discussing, and this will be what we call standard position. This will be the position that we use most frequently moving forward. But do remember that when we're discussing bearings, a lot of times north or 0 degrees will be the positive y-axis, and we'll be moving clockwise from there. So the triangle we're going to work with today will be a right triangle. It will have an angle of theta that will be an acute angle between 0 and 90 degrees. We're going to label out 3 sides to this. We're going to label out the side across from the 90 degrees to be the hypotenuse, the side across from the theta to be opposite, and the side next to theta to be adjacent. Be aware that there are 2 adjacent sides, however, one of those will be labeled the hypotenuse because it's across from the 90 degrees. Within this, we're going to define our 3 primary trig functions. First, sine, which is S-I-N-E, will be abbreviated S-I-N. The sine of that angle theta will be the opposite side over the hypotenuse. The cosine will be abbreviated C-O-S. That will be the adjacent divided by the hypotenuse. And finally, tangent will be the opposite divided by the adjacent. A critical word here for us is going to be ratios. These are trig ratios. So those are the 3 that we're probably most used to. We're now going to work with some reciprocal trig functions. Reciprocal meaning that we're going to flip the ratio. The flipped version of sine will be called cosecant. And the cosecant will be abbreviated CSC. The cosecant of theta, instead of being opposite over hypotenuse, would be the hypotenuse over the opposite. The reciprocal of cosine will be called the secant. The secant will be abbreviated SEC of theta is going to here equal the hypotenuse over the adjacent. And finally, the reciprocal for tangent will be called the cotangent, and the cotangent will be abbreviated COT. The cotangent of theta will equal the adjacent divided by the opposite. So now here we have 6 primary trig functions, and they are related through reciprocals. One point of confusion here, cosecant is not the reciprocal of cosine. Cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and then I think it's pretty clear that cotangent and tangent should go together. Another point of note here, when using our calculator, it would be very easy to say that sine to the negative first of theta is the same as the cosecant of theta. If we pull up our calculator, you can see the sine button has a blue sine -1 above. That is not the same as the cosecant. These are not equivalent. The sign to the -1 would be called the arc sign or the inverse sign. We'll discuss that later in more depth, but that is not equivalent to the reciprocal of sine. We're still going to focus on our primary three, sine, cosine, and tangent. Cosecant, secant, and cotangent have limited uses. There are uses, but they are somewhat limited. We're going to work through this idea that trig functions are just expressed as ratios. And as part of that, one conclusion that we can make is that scale is irrelevant. It does not matter how big a triangle is. All that matters is the shape of that triangle. The magnitude is not relevant here. The discussion of these trig ratios will be based on the shape. We're going to see that here in our first problem. I'm going to ask you to find the 6 trig functions for a 45, 45, 90 degree triangle. These should all say degree here. If you're going to utilize your calculator here, make sure your calculator is in degree mode. I am not giving you the dimensions of the hypotenuse or of the two congruent sides of this triangle. I would like you to define a 45, 45, 90 triangle. I'd like you to define one of the acute angles as theta. The other one will clearly be 45 degrees. We have two legs that are congruent, and then we have a hypotenuse. At this time, come up with a hypotenuse length that you'd like to work with. I'm going to use a length of 8. When we go back to our equation involving a 45, 45, 90 triangles, which is the hypotenuse equals √2 times the leg, we can now determine the lengths of those two legs. Or we could use Pythagorean theorem. So I'm going to plug in 8. I'm going to now determine that each leg would be 8 divided by √2. 8 divided by √2, once we rationalize that by multiplying by 1, will be equivalent to 4 √2 for each leg. So we've got 4 √2 and 4 √2. Yours will be different if you chose a hypotenuse that is not 8. Now we're going to come down and we're going to find the sine of theta, the cosine of theta, the tangent of theta. We're also going to find their reciprocals, which will be the cosecant of theta, the secant of theta, and the cotangent of theta. So for me, the sine of theta will be the opposite, which is 4 √2 over 8, which will simplify to be √2 over 2. The cosine will be the other 4 √2, the adjacent 4 √2 over 8, which will simplify to be √2 over 2. The tangent will be the opposite over the adjacent, which will simplify to be 1. What you should find is no matter what you put in there for your hypotenuse, you should get the exact same ratios here, which goes back to my point that the scale doesn't matter. It doesn't matter the magnitude of your triangle, but rather the shape of your triangle. For cosecant, we would do 8 divided by 4 √2. We would then have to rationalize that denominator by multiplying by 1. We get 8 √2 over 8, which would simplify just to be √2. That's one way of finding the reciprocal. Another way would be just to flip its corresponding ratio. So for secant, I could flip this √2 over 2 to be 2 over √2, rationalize that denominator. I would get 2 √2 over 2, which would just be √2. This is particularly easy for cotangent because if I were to flip 1 over 1, I would get 1 over 1, which is just 1. Another type of problem that we're going to do is just going to have the direction simply solve the right triangle. In this, we're going to need to establish a standard. Our standard right triangle will have a 90-degree angle. Across from that 90-degree angle will be a lowercase c. We're going to use the Greek letter gamma to represent that 90-degree angle. We're then going to fill out the other two angles with alpha and beta. Across from alpha, we'll call that length, or that side A. Across from the angle beta, we'll call that length, or that side B. So when we say solve the right triangle, there's going to be 6 things that we're going to need to solve for. The length of A, the length of B, the length of C, and then the measure of angle alpha, the measure of angle beta, and the measure of angle gamma. In order to do this, we're going to need two pieces of given information. Here, we're going to be given that alpha is 37 degrees, and we're going to be given that C is 5 inches. From there, we're going to be asked to find what are the lengths of side A and the lengths of side B, and then also what are the measures of beta and what is the measure of gamma. Some tools that we have here will be the Pythagorean theorem. We're also going to have trig, and finally we're going to have that the angles will have a sum of 180 degrees. There isn't a right tool to use, but those tools will be the ones that we need. One thing that will be known is that gamma will be 90 degrees. It's going to be opposite the hypotenuse, and therefore it will always be our right angle. We can then use the fact that 37 plus beta plus 90 will equal a sum of 180, and therefore beta would have to be the complement of 37 degrees, which is 53 degrees. We now are going to have to bring in the lengths here. To find either A or B, I would stand at a certain angle and use a trig ratio. So if I'm standing at angle alpha and I did the sine of alpha, that would be equivalent to A over C. Well, I know that the sine of 37 degrees would have to be equivalent to A over my C value, which is 5. A would equal 5 sine of 37 degrees. I could find that in my calculator. I find this to be approximately 3.009. For my final unknown, which is B, I could either use the Pythagorean theorem or I could use trig again. I would recommend using trig. If I used the cosine of 37 degrees, that would equal B over 5. So B would equal 5 cosine of 37 degrees. Using my calculator, I could find my B value to be approximately 3.993. The reason I recommended trig here is because in each of these three steps, the only information I used was the 5, the 90 degrees, and the 37 degrees. And therefore, all I used was given information. At no time did I use a found answer to find another answer. This will help me eliminate rounding errors. It will also help me eliminate compounding errors, meaning if I got one part wrong, I wouldn't necessarily get the second part wrong as well. Something of note here, this is very close to a 3, 4, 5 right triangle. It's a Pythagorean triple that we learned back in geometry. It's not precise, but essentially a 3, 4, 5 Pythagorean triple will have angles of very close to 37, 53, and 90 degrees. The problem I'm going to leave you with here is solve the right triangle. I need to give you two pieces of information. The pieces of information I'm going to give you are that alpha is 20 degrees and side A is equivalent to 12.3 feet. From there, you should be able to find what angle beta and gamma are, as well as the lengths of side B and C. Be careful when we go back to our standard that alpha and A must be opposite, beta and B must be opposite, gamma and C must be opposite when finding these missing sides and angles. Good luck.